Thank you. What an amazing location. And yes, you guys chose the perfect place. Also, I know these are friendly mathematicians we're dealing with because there is a periodic table right there, which is, I think, maybe unique for a mathematics institute. Okay, so I changed the title a little bit, but it doesn't matter. Okay, so I must thank these guys for the work that they do. These are people in my lab. I just advise them. They produce the science. And it's been great. And of course, I also thank the funding agencies for as long as they exist for giving us the opportunity to do this stuff. Okay, so I didn't know where to put this slide. I thought maybe the first slide would be good, right? Nomenclature. Let's see. Also, I shall say that this talk really is on the numeric side of things and less on the theory side of things. But, you know, hopefully you'll still enjoy it. Okay, this is the 1RDM. That's how I'm going to indicate it. This is the external potential. If you wonder what that is, I'm just going to consider external potentials of this kind, which is the interaction of electrons with point charge nuclei. When in the, let's say, unlikely case that you see this, and then I mean a non-local external potential, which is a weird thing. But in chemistry and physics, sometimes non-local external potentials are considered when pseudopotentials are used. Let's say the 2RDM is the big gamma. The R3 factor RDM is this guy. And the correlated part of the 2RDM is this guy. OK. Also, I will show you ways to learn reduced density matrices. But it'll be a little subtle in the sense that I'm not going to be so clear about what I'm learning and just want to be upfront. Sometimes I will show you results where I learn the Kohn-Sham RDMs. And sometimes we'll transition to a part of the talk where I'll show you wave function methods, RDMs such as CASCI, when we can afford it full CI, and so forth. And of course, depending on what I am learning, the unrepresentability conditions that I wish to impose may slightly vary. OK. OK, so what drives me is essentially this statement here. With the current computational methods, may those even be DFT? May those even be approximate DFT, right? Practical DFT. Reality is still, I would say, 95% unreachable, yes? This is what reality looks like. If you're wondering what these are electron microscope pictures of a nanowire, self-assembled nanowire. And I forget the precise makeup of this. I believe this is aluminum oxide, doped, which is used for photocatalysis. Experimentalists come to me and ask me, I would like to know about the optical spectrum of this, and when I put it in this solvent or that solvent, how it works. I'd be lying to them if I told them that, yes, I can, we can totally tell you, predict what will happen. Many times we can, but often, in the majority of cases, we can't because these systems are too complicated. And they're too complicated because they're too big. And when they're too big, even DFT, which scales cubically with system size, has trouble. So we are after the electronic structure of these realistic systems. And this slide I probably can skip. I think we have heard enough about what are the important quantities out there. In my lab, we tackle electronic structure in 3 ways. And each one of these ways is aimed at making a method that is useful for those system sizes that are currently unreachable. So the first one that we look at, that we have looked into and that we still develop, is orbital-free DFT. It's essentially a reformulation of Kohn-Sham DFT where we exploit an additional map between the Kohn-Sham system of non-interacting electrons and a bosonic Kohn-Sham system of non-interacting bosons. That map, of course, involves, every time there is a map, it involves an approximation. So from the interactive system to the Kohn-Sham system, you have to approximate the exchange correlation, functional end potential, and between the Kohn-Sham system and the boson Kohn-Sham, the Pauli potential. Okay, so this, essentially having a boson wave function is much easier because everything is essentially all the electrons are in a boson condensate type system that is more computationally amenable. However, there is this extra approximation. Okay. The other thing that we do is density embedding. Being a chemist or being raised as a chemist, I'm really after molecular condensed phases. And mathematicians, this probably means nothing. But imagine water, liquid water, where you have a bunch of molecules. And each one of these molecules interacts with the other, but maybe not as strongly as the atoms within a molecule interact with each other. Okay? Then if I have that situation, you can see that I can perhaps partition the system into several interacting Kohn-Sham systems, which are then interacting between them using orbital-free functionals. Okay. An intuitive way to see this is that we have an additive energy, which is evaluated accurately, and a non-additive energy, which is approximated. This, I think, is the ultimate method. Actually, we have showed this, that it is the ultimate method for molecular condensed phases. Parallelizes wonderfully, and it is still very accurate, because these non-additive functionals, we have versions of these non-additive functionals that are very good. And then the third way that we go at it is machine learning. This is the newest of our research avenues, and I'll talk about this today. But first, I wanted to make the point that current traditional approaches are inherently flawed. I think I've already kind of made the point that DFT, but even already DFT is too expensive. What about the best possible version of DFT for molecular condensed phases, like subsystem DFT, what I mentioned before? In this graph, you see the computational scaling of subsystem DFT. And as we increase the system size, this is a bulk CO2, fluid CO2. As we increase the system size here from 32 molecules to 256 molecules, I also increase the number of CPUs from 64 to 512. So it's a proportional increase. If you have a linear scaling method, you get a line. Yeah? If you don't have a linear scaling method, you don't get a line. Now, subsystem DFT reaches this line, which essentially tells you you have just about the best possible electronic structure method for this problem. Problematic is that it requires a self-consistent field step, meaning this molecule, DFT, requires an iterative algorithm to solve electronic structure for each of the subsystems. In this case, it was up to 256 subsystems, but you can imagine reality, you need to consider 10 to the 6 subsystems at least, or maybe 10 to the 6 is enough. Now, needing to solve an iterative algorithm means that you need to assign it a considerable amount of computational resources. In the simplest of cases, one CPU or one unit of computational resource to each subsystem. But when you have 10 to the 6 subsystems, 10 to the 6 CPUs, you're looking at mega supercomputers. So what I'm telling you is that even in the best case scenario, we really need mega supercomputers to solve systems that have a resemblance to reality. Okay. Now, you do one calculation if you have 10 to the 6 CPUs. What if you want to solve an actual problem, you need to run a dynamics or something that requires sampling, then you may need to run thousands of calculations, which really makes you go up from exascale computers up to the next scale of computers for these methods to be useful, you really should consider a zeta-scale computer, yes? Okay, well, you see what people say about zeta-scale computers. Okay, 2023, but I think pretty much the common wisdom has unchanged. If a zeta-scale computer were assembled using today's supercomputing technology, it would consume about 21 gigawatts, or equivalent to the energy produced by 21 nuclear power plants. And I don't know what your, can I call it ethics, how you are guided in life, but I need to pay attention to this, and if I devise a computational method, and if my goal is realistic systems, I have to come to terms with this. I'm not saying that zeta-scale computers may not be useful. Certainly they would be useful, but probably not for what I want, what I need. Okay, so let's look at machine learning. And what is that we learn? Well, we need to learn quantities that are rich in the amount of information that they deliver. And I think this point was made already, that the reduced density matrices provide a richer set of information than just the density. You could say, well, the wave function would be really the better quantity, but its complexity and essentially is too complex of a quantity to just learn. Although I'll show you that there's been a successful learning of wave functions quite recently. And whatever we do, whether we learn any of these, whatever we do has to rest on rigorous grounds. I don't want to just start learning something and not knowing whether what I'm learning can be done. Okay. So we look at the Hohenberg and Kohn theorems in general. These theorems provide you with maps. And the maps involve the external potential with a quantity of interest. In this case, I'm showing you 4 possibilities. A map between the external potential and the wave function. You may think, oh, it's useless. Why would you even go there? Computationally, of course, theoretically, you can do whatever you want. Why would you even go there? Until this paper came out late last year, where they were able to encode a quantum Monte Carlo wave function onto a deep neural network. Okay, maybe the jury is still out. We still don't know whether that paper is as good as it sounds, but it has been reported, right? So it's these are molecular wave functions, ground and excited states. So it's something to pay attention to. What I thought would be the best way to go about this is to learn the 1 RDM, or even maybe learn the 2 RDM, if that is a possibility. For the 1 RDM, we have some published results. For the 2 RDM, we're still working. But the field is not, static. There are people working on it, particularly Mazziotti. I apologize, I use his Italian pronunciation to his name. And of course, one can imagine exploiting the map, connecting the external potential with the electron density, and this is very useful. You can imagine already, if you could predict the electron density of a protein, you could already improve dramatically the way drugs are developed. And so this is already very useful, and many people are working on that. Okay. Now, what am I learning here? I want to learn the map between V and gamma. Essentially, I would like gamma to be a functional of V. This has been mentioned many times in this workshop. You have this loop where V gives you a Hamiltonian, Hamiltonian gives you a wave function gives you one RDM. The question is whether this is bijective. I think there was some discussions early today. My point is that for a functional dependence, it doesn't need to be bijective. All I need is, and I always think about in terms of just functions, I just need a single valued function. I need to be able to just have a curve where v is on the x and gamma is on the y. Because if I have a curve, I can try to fit that curve, yes? So yeah, we have that relationship. We know it is single-valued. Great. But of course, there may be the possibility where you have the same gamma produced by different v's. But that doesn't concern me at all. Okay. So you can imagine what I do is just simply running a regression. Now, the critical point here is to find enough to find a smart way to get your training set where you have essentially pairs of gamma and v, and then find a regression. We pick a kernel ridge regression for this task. Now, in effect, that means using this expression, this functional relation. This is pretty standard for regression methods. The point here is that to find these betas, one needs to essentially do a matrix inversion and get, so this case, the kernel, we can use the linear kernel, which is this one, or any other kernel. We also use the RBF kernel. The matrix that we're going to invert is this one. We never actually invert the matrix. We never actually do this because that matrix can be singular or can be singular. And so we just solve a linear problem. We just solve m beta equal gamma. Okay. So imagine you do this. You have a regression that, given a v, gives you a gamma. You wonder, okay, what should I expect? Well, these RDMs are approximate because they're not exact, right? They come from a regression. And so one can write that for any predicted one RDM will look like this, where gamma 0 is the true real RDM and epsilon gamma prime is the deviation to the true RDM.
Yeah, can you go to the previous slide again?
Yes.
Sorry, I just want to make sure that I'm on the same page with you. So the VI are...
VI...
That is data that you have?
Yes.
Okay.
Yes. So I take my system, I find a collection of external potentials, and then I compute gamma with a method of choice, and then I run that regression.
Is it updated, or is it just like you take like a set and you work from there?
You take a set, you work from there, and the trick is, how do you pick that set? Yeah, we'll discuss it. Okay, so the point I want to make here is that if you have a certain error, epsilon, in your predicted 1RDM, your energies will actually be accurate to second order. And this is something that it's almost like always the case in electronic structure. If your wave function is accurate up to first order, your energies are accurate to second order. And same here, because we have that gamma 0, in this case, we're assuming is the gamma that minimizes your true energy functional, and therefore this derivative is 0. And all you're left is with a quadratic part. Okay. Now, I am predicting these gammas. I am not searching a gamma. I'm not minimizing a functional, which means the accuracy of the method really resides in how accurately I can predict the gamma. Not so much in whether this gamma is exactly n-representable or not. We'll see that actually n-representability is important. But there is no such a thing as variational collapse here. Yeah? So in some sense, maybe the idea of this slide is to say that for RDMs, maybe even 2 RDM, maybe machine learning is the way to go and not a variational search. So if I came up with a functional, imagine I come up with a functional, and then I minimize that functional with respect to gamma. For the 1 RDM, it's easy because these n representability conditions are easy for gamma. But imagine you have the 2-body gamma, and you minimize the energy with respect to the 2-body gamma. If you don't impose correct n representability conditions, you would inevitably find energies that are below your variational minimum, and that's a problem. But you're almost guaranteed to be below your variational minimum unless you have all the sets of n representability conditions satisfied. Here you just go by this criterion, and you say, okay, I'm going to leave the accuracy to how well I can fit my RDMs. Yeah, but I get your point. Okay, so we put this together into a code. This code gets the training set, learns this map between external potential and 1 RDM. If these 1 RDMs come from Kohn-Sham DFT, then we can, or a mean field method, then we can just simply use quantum mechanics, or the mean field method, definition of the energy, to get energies and forces. The next few slides will show you what we do for not mean field methods. If you have energies and forces, you can run ab initio dynamics, relaxations, and because you have gamma, you can get expectation values of 1-electron operators. Okay.
What is the mean field theory, for example? This E of gamma.
What is it?
So gamma here is idempotent.
Yes.
And then you mentioned some mean field theories, but
yes.
What would be the example of something that you use?
Yeah. So you'll see later we use essentially any flavor of DFT. We haven't done Hartree-Fock, but no reason to believe that it wouldn't work for Hartree-Fock. Okay. This maps onto the code. If you are into this kind of simulations, you will recognize some of these names. What can I say? Yeah, important in this code is how we handle this training set and how we carry it around. And how we share or make available the models that we generate. One thing to remember here is that when you pick a molecule, you pick a method, like a DFT method, for example. You pick a basis set. Then you have a model. And the model is, in some sense, restricted to all of these restrictions. Yeah? Okay. So I can tell you the RDMs can be learned very accurately. We can predict band gaps and orbitals. We can predict them in the region of external potentials near the training set, but also outside. And I'm showing you some examples so Kasia can see. In this case, we have LDA. And this is methanol. And this is propanol. What you see here are the HOMO and the LUMO of methanol when the OH bond has been stretched. Okay. If you look at this, what I show here is the gap, meaning the HOMO-LUMO energy difference, as a function of this stretch. The green histogram is where the training set is. Okay, so naturally, it'll be around 1 because these OH bonds in alcohols and water just about 1 angstrom long. So you have your training set there, and then we'll get you to how we build this training set. You can see that what we have from the actual method here and here, very similar to what we get from the predicted 1 RDMs here and here. To get these orbitals, we take the RDMs, we build the Hamiltonian, we diagonalize it, we get the orbitals. Okay? It's like a proxy to how good this RDM is. Same for propanol. And what you see is that this gap is actually predicted much farther away from the training set. Okay, so yes, the model is restricted to the particular method, molecule, basis set. But at least it's accurate. But how accurate? Seems accurate, but how accurate? Well, so accurate that we can run molecular dynamics with these RDMs. Just to give you an idea, chemical accuracy is something like 1 kcal per mole, something like this. And yeah, 1 kcal per mole would not allow you to do this. You would get very wild dynamics that would take your molecules in completely wrong directions. To get stable dynamics, meaning to get energies and forces directly from the RDMs, you need an accuracy that is at least 3 orders of magnitude better than chemical accuracy. So in the chemistry community, people are after chemical accuracy. But in the electronic structure community, we should be after what I call SCF threshold accuracy. SCF threshold, remember the self-consistent field that is used to solve for the electronic structures, that is orders of magnitude smaller than chemical accuracy. So that's what you need for this. And of course, we have the RDMs, so we can compute spectra. And this is all entirely from predicted 1 RDMs. And for propanol, the same. And by the way, here, I guess I'm failing to tell you what this is. Here is the simulation time. And on the y is the fluctuations of the, essentially, electronic energy. If you add these fluctuations to the kinetic energy of the nuclei, you will get a flat line if you run so-called NVE dynamics. But, removed the kinetic energy of the nuclei, you get fluctuations. And what you see here is that these machine-learned versions, and they differ by just a detail, which are really not even worth mentioning. If you see these fluctuations of their true functional are recovered by the machine-learned one. I mean, this is just a testament to the fact that, okay, it's not perfect, but close. Even a discrepancy of machine precision, like 10 to the minus 14 or 15, eventually would lead to different dynamics, yes, of the molecules. So the fact that we're keeping these fluctuations essentially on sync for quite a while is good. And in case you're wondering, we can also do things like propanol, which you can imagine this is very hard to do because propanol is very floppy, flops around, meaning there are many, many more external potentials that are relevant for propanol than for something like benzene, which is kind of static and stays like that. Okay. Okay, so now finally I can answer your question. Yes.
Previous slide.
Excuse me?
On the previous slide?
Yes.
So you had like multiple, I'm not a chemist, so I don't know exactly what's going on.
Yeah, no, it's fine, it's fine.
But like, so these are all supposed to be simulating the same thing, but they're kind of off.
They are shifted just for visual so that you can see what's going on. And you can see that, you can count the peaks and the valleys and make sure that they occur right about the same point.
Like, but is that any actual difference, significant difference in the, like?
So that's a fluctuation of the energy which you expect because the electronic energy is not conserved along the dynamics. is the electronic energy plus kinetic energy of the nuclei that may be conserved if you run an MVE calculation. So here you expect this to fluctuate. The point I'm making here is that these fluctuations are the same whether I use the machine-learned version versus the original, traditional electronic structure method in blue.
How many molecules are in your simulation?
One. Yes, yes.
Sorry. How do I interpret the accuracy of the V3-lib ML case, like the 100x?
Yeah.
Solid and dash.
Yes. It's a great question. It's a great question. In fact, this was not in the original paper that was submitted. But the referees sometimes are very practical people, and I think in a good way. Like you want to show the experimentalists that your method works. Yeah, you don't just want to have a method that 20 people realize that is great, and that's it. So we had to put this. We had to show that what we do is kind of realistic, and the experimentalist was happy because you see that the peaks occur at the same correct frequency. These are peaks that arise from the vibrations of the atoms in the molecule. Okay, like natural frequencies of vibration. Yes, first there and then here.
So you said this is a one-molecule simulation?
It's a single molecule, yes.
Early on in the presentation, you had like a comparison of two methods.
Yes.
And the middle one, I didn't really understand what's going on at first, but the middle one was kind of like a multi-scale model.
Yes.
Where it was like you had, the
Subsystems, yes.
The subsystems were individual molecules, right?
Yes.
So
So you could run my lab. I mean, it's exactly what I'm trying to do now.
Okay.
Yeah.
It relates to the previous question. So you, again, just to clarify, you train on the same molecule with different geometries. This is your training set.
Yeah, essentially, yeah. So you have to pick a molecule that you're interested in, and pick a method, pick a basis set, learn that. So I see how you can be kind of turned off, because machine learning usually is something that applies, like you want machine learning to be transferable, blah, 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 blah. No, I don't want that, because I want an SCF accuracy gamma 1.
So the one matrix has less information in it than n squared, right? Because it's a sum of products of orbitals. I mean, my question is how you represent the one matrix.
I guess I'm not telling you. In chemistry there are well-developed methods to discretize, this one particle Hilbert space. So we're using Gaussian type orbitals, and I'm using literally the upper triangular part of gamma 1 in a given basis set.
But you have to then take care of how the basis set rotates.
Great question. Okay.
There are some invariances there.
Yes. Is that clear to everybody, this question? Yeah? Because if you have a GTO basis, any atomic orbital basis, it will have angular momentum. And when you rotate the molecule, the matrix elements will rotate, but they rotate in a very trivial way, yes? They rotate, if you know the three Euler angles, you can get. So here's the thing.
Internal rotations, right? It's not just the.
Oh, internal rotations, okay. Okay, internal rotations, different story. Let's talk about like global rotations, yes? Laboratory rotation, if you wish. So I don't know if you have recently seen talks by Michele Ceriotti. He has built a career on equivariant kernels and equivariant methods. These are methods that, exactly what you're talking about, if you rotate your target, the method detects the rotation and provides a prediction that is rotated accordingly, an equivariant prediction. Spent maybe 10 years of his life working on this. Very successful, very smart. But in order to render a method, equivariant method, you have to do Klebsch-Gordon, Wigner D matrices, rotations. You have to do some work, yes? Making the machine learning apparatus more expensive. It turns out if you just multiply by 10 the number of training set points, you get equivalent accuracy, and it is cheaper. So now he's at a stage where he's reconsidering his thoughts. And he being the guy who has really pioneered that, I can tell you, we don't have an equivariant model here. We have a very smart way to rotate these molecules, not smart way, I should say stable, robust way to rotate this molecule to some sort of common rotational frame, but it's never going to be perfect. So that imperfection are learned by adding
So you
training.
get the learning to learn the symmetries.
Yes, essentially yes. Essentially yes.
Kernel ridge regression is scaling is cubic, right?
Yes. Oh, you'll see the computational cost. Yeah, it's a good point. So this training set, and that goes to your question, how big is this training set? Yeah? Imagine you have a molecule like this. It naturally vibrates. And there is something called normal modes of vibrations, which are essentially the principal directions in which a molecule can deviate or move away from its equilibrium geometry. So these normal mode of vibrations grow in number linearly with the number of atoms. So here for benzene, you have this many. And what we do, we use these normal modes of vibration to generate a volume in this dimensional space given by these normal modes. And then we randomly drop some dots in this volume, subject to the constraint that these dots are separated by at least sigma, which is a user-defined threshold. So you sample this volume accordingly or as uniformly as you can. The size of this cube is given by the temperature that you're after. So molecules vibrate more when the temperature is higher, so they sample a configuration space that is bigger as the temperature goes up. Okay. What is usually done is to run an ab initio dynamics, let the molecule run in time, evolve, and then cluster the geometries that arise from an ab initio dynamics, and then take the geometries that are important from this clustering and build a training set. I want to do it differently because I want to avoid, at all costs, I want to avoid an ab initio dynamics carried out with an expensive method. Totally avoid ab initio dynamics. I use this normal mode idea, and these are the distributions of normal modes, how they're vibrating. In tan, AIMD, in blue, our sampling, and our sampling is pretty much on top of the ab initio dynamics sampling, with the exception of this guy. But we don't care, in the sense that that didn't give us so much trouble. Still pretty good. Yes. These are actually these are vibrations that are scaled by the energy of the normal mode. It's a way to essentially write your vibrational energy as a sum of oscillators, and all these oscillators have
Normalized.
Exactly. The vibrational constant is 1 for each one of these oscillators.
But then my question is maybe like how large is your box for 300 Kelvin?
Oh yeah, that depends on the temperature, and on the vibrational constants on this normal mode.
For instance, for benzene here, so what would it
Yeah, I have to check, but comes out. You do a vibrational analysis.
few angstrom, few tens of angstrom?
Oh no, it's in the order of 1 angstrom, or less. And it depends, it changes depending on the atom type, right? So the hydrogens will roam more than the carbons, right? Because they're lighter. So how many of these do we need? Like I said before, chemical accuracy, 1 kcal per mole. For benzene, maybe 20 structures? 20, maybe? SCF accuracy, what we published is this line here. We published this paper with close to 14,000 structures for benzene. Now we can get away with some tuning. We can get away with about 1,000 structures for benzene at 300 Kelvin. Raise your hand if you think that's way too many structures. Don't be shy. Raise your hand. Nobody? Really? I was expecting a mass. Hand raised. People, when I say 14,000 structures, they're like, you can see them in their faces. They're like, what?
14,000 structures, but what is one structure?
One structure is one benzene molecule with a given structure of the atoms, and I compute the external potential in this basis and in a given basis and the 1 RDM for a target method. So you can see that you need, the more you need to calculate, the more training points in your training set, the more calculations you have to run, which is costly and makes you wonder, how long does it take? Maybe I can just run the regular simulation rather than training a machine learning model. Yes? So 14,000 structures, is that a lot? If you were into the chemical physics of raw vibrational spectroscopy, which is a spectroscopy that probes vibrations and rotations of molecules, you would be fitting potential energy surfaces of molecules like this to a very high accuracy, arguably similar accuracy as this. And that community routinely uses between 50 and 150,000 structures per molecules of this size.
Sorry, when you say there is a factor to take into account the rotations, should we to multiply by 10 this training set size?
Why by 10?
Because you said you fit, you don't use an invariant covariant kernel. So
good point, good point. Well, this is the entire set.
The entire set.
Yes.
Okay.
Sorry, can you briefly, and I'm sorry if you already explained it, explain the different lines, because the first one is the ML, one is cross delta, and RBF is radial basis function.
Yes, okay, so these are two different methods two different models, machine learning models for the RDM. One we call just gamma, and the other one is divided into two pieces, gamma and delta gamma. It's like a delta learning on top of the learning.
Goes with the gamma 0?
This one is better, or was better in our first iteration. It allowed us to really reach SCF threshold if we threw enough points.
There are two models for gamma and delta gamma, or gamma 0 and delta gamma, or?
Oh, so this gamma pita is essentially a single kernel ridge regression to get gamma. This gamma p plus delta gamma is two kernel ridge regressions. And this one is the single kernel ridge regression with the RBF kernel that already gets you here. Yes. Okay, so answer is no, these are very forgiving training set sizes. Yeah. Okay. So if I compare how many of these training set points do I need compared to the cube of the essentially number of atoms, I go back to your question, I think. This method is cubic in computational complexity. So then you may wonder, why are you doing this? Let me show you this, where essentially the prefactor is cubic, but what is the prefactor in terms of training set size? Prefactor is essentially 1 for small molecules with weird cases like internal rotation, like you had mentioned, for which we have to increase the training set size by however many important conformations are there. But then it drops. So if you look at the blue is the kernel ridge regression with the RBF kernel. Then it drops, this complexity drops quite a bit for larger molecules. Even a molecule as big as this which, by the way, I mean, I don't know what you typically do, but when my students said, hey, can we do biphenyl? I just told them, no way. It will never work for biphenyl. It's too big. You will need millions of training structures, and it will not work. It turns out it works quite wonderfully with, and you'll see later, with about 30,000 structures. And here is, for biphenyl, the computational cost. And here, everything I talked so far is to do with DFT, yes? So if DFT costs 1 for this molecule, this machine learning method costs 0.2. Whether I use 15,000 structures or 30,000 structures, the cost is negligible, negligibly different, sorry, yes? I'm not prepared to talk about this right now, but just these three ones. So we are reduced the prefactor, yeah? Yeah, okay, that's, for small molecules like this, that's pretty good. And this is DFT. Yeah?
How well, sorry if I interrupt. How well it does when you use this for predicting? You were showing some spectral.
Tell me again, sorry.
So when you use this model, trained model, compared to DFT for predicting something that you were not trained on, you were looking at the spectra.
That's the cost of the prediction. And the
accuracy.
The accuracy?
Accuracy of your, how well compared to if you predict a, you were earlier showing some spectral lines. If you use DFT for predicting that?
Oh, on top.
Okay.
Literally on top. Yes. No difference. I plug this molecule into Gaussian, I get an RDM, and I compare it with mine. It's the same. Okay. Okay. So should we go beyond mean field? Yes. Yeah? I think that's actually where things get more interesting. And I don't know how long I'm going. Am I going too far, too slow?
If you ignore that we started late, you have like 1 minute left.
Oh my God. Why am I speaking so slowly today? I don't know. Okay. This was the more interesting part. If you are after correlated 1-RDMs, you need to be able to predict the occupation numbers of these RDMs. And when you have a mean field method, these occupation numbers are easy. Just the M is idempotent, so they're 1 or 0. We can use this iterative method to purify our predicted 1-RDM if there are some small deviation from purity. What about correlated RDMs? Well, we were working on totally different things. We're looking at, well, now looking at this workshop, maybe not so totally different, looking at static correlation functionals. And we realized that actually the Fermi-Dirac distribution will fit your 1-RDM occupations almost perfectly in almost everything you look at. And I'm talking about ground states of molecules. Okay, so we just use the Fermi-Dirac distribution to purify our 1-RDM occupations. Surprisingly accurate method, and I would wish that I knew why. But that's what it is. Maybe you can tell me why. So, same idea, build a training set near the equilibrium geometry. I add 1 point at dissociation, and I can predict the occupation number distribution as a function of bond stretch, in this case for a water molecule stretching. But if we stretch it in a really nasty way like this, where bonds are broken and then formed, and where the occupation numbers of the Futsi method have a discontinuity, yeah, we don't catch that discontinuity. We don't catch it. I'm okay with that. And we can run dynamics, yes, we can, at the cost of learning another map, the map that takes you from gamma to E of gamma. Okay. Too bad, because now I had a nice story on 2 RDMs, but I don't want to take advantage of your time. Suffice to say that for the gamma 2, the same procedure works, but we were not able to make it work for the full gamma. But for the correlated gamma, yes. And in fact, there are reasons to believe that we may be able to even reduce the training set size dramatically if we are only after the correlated part of gamma 2. And I don't want to. Okay, yes, a result of gamma 2 is that we can train at 300 Kelvin and predict totally stable dynamics at 600 and 700 Kelvin. And this is something we couldn't do with gamma 1. You know, having gamma 2, you get access to all sorts of observables that are interesting. And the computational cost is less than MP2, or just about MP2, but much more accurate. And then we also can do condensed phases, but I'm sorry, I don't have time to tell you that. And thank you.